All right, so today's topic is a single topic, and it focuses on the main idea of something called an ICE table, a monitoring for the initial conditions, changing conditions, equilibrium conditions. And where it stems from is this fundamental idea here. Thus far, when we have calculated equilibrium constants, whether they've been KPs or KCs, the calculating that we've been doing has involved us taking equilibrium concentrations of each thing and plugging them into the appropriate level. And that kind of work it's pretty easy to do. I mean, if we know how to create a equilibrium expression and we know what we can include and what we cannot include in that expression, then plugging in values and doing math is actually the easy part. But when we actually go to use this kind of information in practice, that's usually not what we end up doing. It's really difficult to know the exact concentrations of our reactant on our products unless we have a little bit of legwork that we do. Now, in the lab yesterday, we saw what some of that legwork can look like. So in the lab yesterday, we created a complex ion, and we were able to monitor the initial concentrations of each reactant and then use spectroscopy to figure out the concentration of the product and work our way through the equilibrium conditions that way. But what if we don't have that information? What if we just have an equilibrium expression and our equilibrium constant? How do we go about figuring out what the reaction species are? How do we go about figuring out what the equilibrium concentrations are? And so that's where we start this morning. What we're talking about here are ICE tables. Now, you might see these referred to as RICE tables, where the R is for the reaction. So reaction, initial, change, equilibrium. Kind of depending upon what text you look at or what resource, you will see both. They'll be used interchangeably. They're talking about the same thing. But what an ICE table does is it's basically an organizer. And in that organizer, we are tracking what are the initial concentrations of each species in the reaction. How do those reaction species change over time? And what are they going to be at equilibrium? Now, as far as the I is concerned, we will always know I. Because if we're setting up the equilibrium ourselves, we know exactly how much reactant to put in and exactly how much product to put in. So from that standpoint, we'll always know what I is. To figure out what C is, we're going to have to call back to something that we did yesterday, the reaction quotient, Q. Now, sometimes it's really easy. If I'm starting with just reactant and no products, it's obvious what's going to happen. The reactants are going to react with each other and make products because there is no product yet. And if I start with just products and no reactants, same thing. The products react with each other and make reactants. The reaction's obviously going to shift to the left. But what about scenarios where we have everything all present already? Well, that's where our Q calculation would come in. We could calculate what Q is for the conditions that we are starting at and figure out which direction it's going to shift quantitatively. And if it shifts to the right, then we know that we're going to add product and remove reactant. And if it shifts to the left, we know that we're going to add reactant and remove product. So that's what the change line is. Now, one thing that we want to definitely include here is that the stoichiometry of the equilibrium does have an impact on the change. If we are doing a chemical reaction where there are two of reactant A and one of reactant B, well, we know that kinetically speaking, that reactant A is going to disappear twice as fast as reactant B because there's two of them and only one of the B. That needs to be reflected in our change as well. Now, in an ice table, I plus C equals E. So my equilibrium conditions are going to be what we expect at equilibrium. I can find those equilibrium conditions by adding together the previous two lines. Now, as is the case in any kind of scenario like this, where we're going to be dealing with some kind of higher level mathematic or something that's very algorithmic in its process, the best way to learn how to do this is to just do lots of practice of it. And so that's basically what we're going to intend to do. And so what we always want to look for is out of an ice table, we need to know a certain number of things. We need to be able to calculate any value of I, C, or E. We also need to be able to calculate the equilibrium constant. But here's the thing. I can't calculate any one of those without knowing the other three. I can't calculate any one of those without knowing the other three. So this is what it means when it says if enough information is already known. I need three of the four of those to find the other one that's missing. Now, most often, those calculations are going to be of the last two. Where we're either going to calculate the equilibrium value for one or more of the products or reactants, or we're going to put everything together and figure out the value of the equilibrium constant. And again, calling back to lab yesterday, that's what we were being asked to do in yesterday's lab. Use the information that we had acquired to solve the ice table itself, and then use the results of that ice table to solve for K. So let's take a look at an example here. Here we have the reaction of nitrogen gas and oxygen gas to make nitrogen monoxide. We are given that the equilibrium constant for this reaction, its Kp, is 1.00 times 10 to the negative fifth. And further, we've also been told that the initial pressures of nitrogen and oxygen are 0.79 atmospheres and 0.21 atmospheres. And so the way that we set up an ice table is pretty similar to this. We start with the reaction, and underneath that reaction, we lay out our initial conditions, our changing condition, and our equilibrium condition. And so if we start here with the initial conditions, what are we told by the problem? Well, we're told in the problem that initially we have 0.79 atmospheres of nitrogen and 0.21 atmospheres of oxygen. We aren't given any information about the nitrogen monoxide, so it's safe to assume that it's not there. And so its initial pressure is 0. Now, if we wanted to, we could set up an expression for Q here. But what we would find is that 0 squared is equal to 0. And it doesn't matter what I divide by after that, it's still 0. So in this particular case, calculating Q doesn't make a whole lot of sense because we know we have no product, which means that we're going to have to make product in order to reach equilibrium. And so our next step would be this one, identifying the change. Since we know that there's no product, we know that we're going to see that this reaction is shifting toward the products. It's shifting to the right. That means that the concentration of the product is going to go up by a certain amount, and the concentration of each reactant is going to go down by a certain amount. How much is that amount? Well, that remains to be seen. But we know that they are going to be losing and gaining in proportion to roughly the same idea. That's what stoichiometry is all about. So based on the stoichiometry, I'm going to lose 1 part nitrogen and 1 part oxygen, and I'm going to gain 2 parts of nitrogen monoxide because the 2 in the balanced equation tells me that the nitrogen monoxide is going to form at double speed compared to the reactants. And so that's what this change line is all about. I look at the direction that the reaction is going to go. Reaction participants on that side are going to gain in concentration, gain in pressure. Reaction species on the other side are going to lose in concentration, lose in pressure. And the amount that they gain or lose is going to be some variable. That's why we're using X here. And that variable can be multiplied based on the stoichiometry of the reaction. Since equilibrium is equal to the initial plus the change, I would add these 2 rows together, and that would give me my equilibrium set of conditions. So at equilibrium, the pressure of nitrogen is going to be 0.79 atmospheres minus some amount that it lost. And the pressure of oxygen is going to be 0.21 atmospheres minus some amount that it lost. And the pressure of the nitrogen monoxide is going to be 2 units that were gained. Now, on its face here, we still really haven't solved anything yet. We've organized ourselves, but we really haven't done anything yet to try to solve any kind of meaningful question about Well, how much did it actually change? Give me a number. What are the equilibrium pressures? Give me a number. We haven't done any of that yet. But what we have to keep in mind is that we do have an equilibrium constant for this. And that value of that constant was given to us at the beginning of the problem. 1 times 10 to the negative fifth. And so what we can do now is we need to go about solving the process. We need to solve for x and figure out what the value of x is. And then we can move on to the rest. Once we know what x is, we can back substitute it and change all of those x's into whatever that value is and find the equilibrium concentrations, or in this case, pressures, for each species. So Kp is equal to 1 times 10 to the negative fifth. And that's equal to the pressure of the nitrogen monoxide squared divided by the pressure of the nitrogen times the pressure of the oxygen. Now, we go back to our equilibrium lines here. The pressure of the nitrogen monoxide is 2x. So that's going to be 2x quantity squared. The pressure of the nitrogen is 0.79 minus x. The pressure of the oxygen is 0.21 minus x. And so what we have shaping up here is everybody's favorite application of Algebra 2. We've got binomial expansion. Yay! And we've got a quadratic formula looming on our hands. So let's go about the first part. Let's do the binomial expansion. So 2x squared, 2 squared is 4, x squared is x squared. For the binomial expansion, we're going to need to use FOIL. 0.79 times 0.21 is 0.1659 minus, or excuse me, times, so 0.79 times negative x, so 0.79x minus 0.21x plus x squared. So rewriting, 1 times 10 to the negative fifth is equal to 4x squared over 0.1659. Combining these two x terms, we get negative 1, so negative 1x plus x squared. Remember, the trick for the quadratic formula is that we've got to get all of the terms onto one side of the equation, and the other side of the equation is 0. So my next step would be to multiply both sides by the denominator here, 0.1659 minus x plus x squared. So 1.659 times 10 to the negative sixth minus 1 times 10 to the negative fifth x plus 1 times 10 to the negative fifth x squared equals 4x squared. The last step would be I need to get the 4x squared out of there, so I need to subtract 4x squared from both sides. So negative 4 plus 1 times 10 to the negative fifth is negative 3.99999 x squared. Now, this is the part of the, excuse me, this is the part of the program where you take careful note of the fact that we have not banned graphing calculators in Chem 106. Because if you have a graphing calculator, there's a good chance you have an equation solver on there. And if you don't, there are wonderful equation solvers on the internet that we can use just as easily. Now, let's say, for the sake of argument, you don't have access to either of those, then you're going to have to use the quadratic equation. Quadratic equation, x is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. Negative b would be 1 times 10 to the negative fifth plus or minus the square root of 1 times 10 to the negative fifth squared minus 4 minus negative 3.99999 and 1.659 times 10 to the negative sixth, all divided by 2 times negative 3.99999. Now, the thing about the quadratic equation, or anything that we would draw off of this, whether it be a cubic or a quartic or whatever, and if you get a cubic or a quartic or whatever, look for two things. Look for, first of all, is there a way to simplify it? And if not, we don't have a cubic equation at our disposal. We don't have a quartic equation at our disposal. Use those extra references. Use an online equation solver or your calculator to do that. But assuming all things as equal here, regardless of what the thing that you have to solve for is, what you're going to find is that one of the answers makes sense in the context of the problem and the others do not. Now, in this particular case, we have a negative number in the denominator. The only way that this makes sense is if we have a negative number in the numerator and that number happens to generate less than 0.21. Because if it's greater than 0.21, that means that we have negative pressure for oxygen. That doesn't make any sense. If the number in the numerator is positive, giving us a negative number there, that also does not make sense. So if we do the work inside of the square root, 1 times 10 to the negative fifth squared minus 4 times negative 3.99999 times 1.659 times 10 to the negative sixth. And then taking the square root, I'm getting 5.15 times 10 to the negative third out of that mess in the square root. And that's after taking the square root. And so with that being the case, I know that negative is going to be the way to go to give me a negative in the numerator. And from there, we would calculate an x value of 6.4 times 10 to the negative fourth atmospheres. But like I said, this is kind of the hard way to go about doing things. I'm not so certain that I like that as an option in most cases. So what I would be seeking to do is I would be searching for something like this, a relatively simple tool where I can plug in my values of A, B, and C. So A was negative 3.9999. B was 1 times 10 to the negative fifth. Negative 1 times 10 to the negative fifth. And C was 1659. And so we throw that in there and we get 6.4 times 10 to the negative fourth, which is also what we got through the quadratic equation. And so like I said to you here, I'm not against you using some technology here to help you with the solving of some of these, especially at the end of class, I'm going to show you a way to cut through some of the nonsense if K is small. And in this particular case, this would qualify. But in cases where K is moderate to large, a quadratic or a a larger function is going to be necessary to do it. And so it's important to see kind of both ways to do it, just so that if you get to that test and you're having trouble getting your calculator to function properly. Now, like I said, if you're using a graphing calculator, there are ways to calculate roots using the graphing function of your graphing calculator, and some are programmed also with quadratic solvers. And if you need help with that, I can help you with that at a later time. But don't be afraid to use something like this. This is, I've been using this one on Calculator Soup for years. It's pretty reliable. So I'm happy that I solved the quadratic equation correctly. But obviously you can see that there's a lot of legwork that has to be done there. And there's a lot of assumption on your part for what is right. Sometimes it works out this way where it's nice and easy to see. Sometimes you got to do a little bit more work to figure out what makes the most sense. But with this x value, 6.4 times 10 to the negative fourth, you can go back to your ICE table now and substitute. And you can calculate the actual values. So 0.79 minus 6.4 times 10 to the negative fourth is, well, 0.7893, but if we're keeping two sig figs, it's still 0.79 atmospheres. 0.21 minus 6.4 times 10 to the negative fourth, 0.20936, but again, if we're keeping our two sig figs, it's 0.21 atmospheres. 2 times 6.4 times 10 to the negative fourth is 1.28 times 10 to the negative third, rounding that to two digits, 1.3 times 10 to the negative third atmospheres. And so one thing that we will see, and we see this often, when our K values are relatively small, but yet our starting concentrations or pressures are relatively large, there tends not to be a ton of impact on those initial concentrations. And one of the last things that we'll talk about today is, when is it okay to safely ignore those changes and to just go off of what we see in the change in product? Because I think we would all agree that if I was able to ignore those minus x's, knowing that they didn't change, the calculation would have become infinitely more simple, because I wouldn't have had to solve a quadratic at all. I would have had numbers in the denominator and 4x squared in the numerator. I can take the square root of something. All right, so that is example one. Let's take a look at a second example. So here we are starting with 0.1 moles of nitrogen monoxide, 0.05 moles of hydrogen, 0.10 moles of water, all in a 1 liter vessel at 300 Kelvin. The question is, what is the value of K if the equilibrium concentration of nitrogen monoxide is 0.062? Now, we are given the equilibrium expression. We want to set up our ICE table. But before we can set up the ice table, we have to understand that that we have not actually been given concentrations here. We've been given molarities. And that's not going to work for us here because, well, molarity and moles are not necessarily the same thing. Now, in this particular case, we're in a 1 liter vessel. And since molarity is moles divided by liters, moles divided by 1 is molarity. But we have to be mindful of that. And you saw that in last night's homework. One of the problems asked you to turn grams and put it into equilibrium terms, calculating Q, I believe. So if you're not given molarity or pressure, you've got to convert what you are given into one of those units. Now, in this case, again, because it's 1 liter, the moles is the same. So this is 0.10 molar. This is 0.050 molar. And this is 0.10 molar. We weren't given any information about nitrogen. So what do we do? Well, it doesn't have to be a product to do that, but yes. If we aren't given information about it, we're safe to assume it's 0. So we have nothing here initially. Since we have nothing here, we don't need to go through and calculate Q. We know that the reaction is going to shift to give us some amount of nitrogen. So we're going to see the reaction go this way, which means we're going to lose on this side and gain on this side. How much do we lose? Well, we lose 2 portions for the nitrogen monoxide because there's 2 in the reaction. We lose 2 portions of hydrogen. We gain 1 portion of nitrogen, and we gain 2 portions of water. Now, we've been told that the concentration of nitrogen monoxide at equilibrium is 0.062. And so from this piece of information, we can actually stop right here. We don't need to fill out the rest of the ice table because we have a means for settling what X is. And it comes from the idea that I plus C equals E. So 0.10 minus 2x is equal to 0.062. Doing a little bit of algebra, let's add 2x to each side. 0.10 equals 0.062 plus 2x. Now let's subtract 0.062 from both sides. So 0.1 minus 0.062 is 0.038. So 2x is equal to 0.038. And so what I can do is, for the terms that are 2x's, I can I can put those in. To get X by itself, which is what I need for nitrogen, I got to divide each side by 2. 0.019 is equal to X. Now that I know what the changes are, I can add those to the initial and figure out the equilibrium values. So 0.050 minus 0.038 is 0.012 molar. 0 plus 0.019 is 0.019. And 0.1 plus 0.038 rounded to the second decimal place is going to be 0.14. I now know the equilibrium concentrations at each of the reacting species. Now I just need to figure out the value of K. K would be equal to the concentration of nitrogen multiplied by the concentration of water squared, divided by the concentration of nitrogen monoxide squared, multiplied by the concentration of hydrogen squared. Nitrogen is 0.019. Water is 0.14 quantity squared. Nitrogen monoxide was 0.062 quantity squared. Hydrogen is 0.012 quantity squared. Putting all of that together, 0.019 times 0.14 squared divided by 0.062 squared divided by 0.012 squared to two significant figures, we have 670. All right, any questions with those first two examples? Okay, so these are probably the two most common applications of ice tables and equilibrium. We saw in the first one where we had to use the value of K and the initial conditions to solve for the equilibrium concentrations. In this one, we had to use the initial conditions and some sort of information about one of the final conditions to solve for the equilibrium constant itself. Like I said, those are probably the two most common applications. All right, go ahead and try this one on your own then. So here I have an equilibrium between iodine reacting with bromine to make iodine monobromide. We're given information about the value of K. We're given information about the starting amount of iodine monobromide. What is the equilibrium concentration for each substance in the flask after it comes to equilibrium? All right, I chose this problem intentionally, and the reason I chose it intentionally is I this is a great way to see kind of, are we just following the same pattern, or are we actually thinking everything through? So first thing that you should notice, if we're making our ice table here, iodine is a solid. So in our expression for K, it would be the concentration of IBr squared over the concentration of bromine. There would be an iodine term because iodine is solid. So what do we do in an ice table when we don't have a reacting participant? We ignore it. So either put a big X over this part of the ice table, or what you can do is just kind of put in a series of dashes here to remind you not to worry about what's going on with the iodine. Because in terms of the equilibrium, we don't care. Second thing, we aren't given any information about the bromine, only the iodine monobromide. So this is 0.5 molar. Most of you came up with that. And most of you came up with the idea that bromine, there's nothing there. But what most of you did, and this is a classic mistake, that is, I'm not fully quite understanding exactly what I'm supposed to do, is a lot of you did this, minus x plus 2x, because every problem that we've done so far, we have added product and removed reactant. Well, it doesn't take much logically speaking to go, well, wait a second, that makes no sense. How do I lose what's not there? So what we have to remind ourselves of is, yes, equilibrium is reversible. It can go the other direction. So in this case, we started with all product. We're going to shift toward the reactant side. So the X and the 2X are correct, but we've got the wrong signs on them. We're going to gain bromine. We're going to lose IBr. My concentration of bromine is X. Excuse me. My concentration of the iodine monobromide is 0.5 minus 2X. And now we go about the business of starting to put this together. So K is equal to 280. IBr concentration 0.5 minus 2x quantity squared, and x in that denominator. If we do the expansion, 0.5 squared is 0.25. 0.5 times negative 2 is 1, negative 1. So that would be minus x, then minus x again for the other side, and plus 4x squared all over x. I'm going to move the x to the other side, so 280x is equal to 0.25 minus, let's put those x's together, 2x plus 4x squared. And subtracting 280 now, 0 is equal to 0.25 minus 282x and 4x squared. So again, here's a place where we would seemingly need the quadratic equation. Rather than go through the rigmarole of doing the quadratic equation again, let's just go ahead and go back to our equation solver here. So our values this time were 4 and negative 282 and 0.25. And the two values that I get, one of them is 70.5, essentially. Well, I can't lose 70.5 when I only had 0.5 to start with, so throw that one out. The other option is 8.9 times 10 to the negative fourth. That one makes a lot more sense. So 8.9 times 10 to the negative fourth is the value that we're going to use. So x is equal to 8.9 times 10 to the negative fourth molar. I can substitute those back in here and over here. And that would give me concentration values, excuse me. Of 8.9 times 10 to the negative fourth molar for the bromine, and 0.5 minus 2 times 8.9 times 10 to the negative fourth, which is 0.498 for the iodine monobromide. Now, an easy way to double check ourselves and make sure that we did it correctly, we can plug those values back into our K expression and make sure that we're getting something in the neighborhood of 280. So with those values, 0.498 squared over 8.9 times 10 to the negative fourth. To two significant figures, I get 280. The actual number on the calculator is just a little bit over 278. So it matches what we were starting with. We know we're on the right track. All right, any questions with this problem? Okay, let's go ahead and take a break. It's 9:10. Let's come back at 9:20. We'll do some more ice tables. I'll also show you a shortcut method that we can use when our equilibrium constants are small relative to our concentrations at the beginning.